Now I continue playing this game with figures. Now I show, using the figures that give a very good understanding how the mathematics of the formulas work, how Quiggin may have gotten the idea of rank dependence, how he got the new idea. So now it is coming. And first I repeat, here was the way to depict expected value, and here was what economists did. They look at columns, they transform columns, and for each point they transform the distance from the point all the way down to the x-axis into its u value. That's how they got the green columns, and the green area, that was the value of the prospect. So transforming distance from point all the way down to the x-axis. Now we see what psychologists did. They flip and turn the figure so that the columns, the heights have to do with the probabilities. Then when they do that transformation, you see they transform, for every point, they transform the distance to its lower neighbor. That's how they determine how high every point should be in this figure. Now, if you compare the brown figure with the green figure, you see psychologists are not doing with probabilities what economists are doing with outcomes utilities. Psychologists do something different. So it's very natural when Quiggin, and I told you Schmeidler independently had the same idea, a bit more subtle maybe, but let's focus now on Quiggin and risk. So Quiggin said, if we want to do really with probabilities what the economists do with utilities and the same mathematical concept, we should transform for every point, we should take the distance all the way down to the x-axis and transform that by a w function. Then we really are doing what economists do with utility. And in mathematical term, then you are having truly a dual functional, but let's not get too technical. That's the correct way to have a dual function at any rate. So Quiggin said, let's try that. So I'll show you the next figure how Quiggin did that. So we start with this figure P1, this is P1 plus P2 plus P1, P3 plus P2 plus 1, and so on. And finally, all the probabilities, they add to 1. So this is how high all the points are. And then Quiggin, using the psychology intuition, we said first we're going to replace the distance of P1 all the way down to the x, but that's the same as the lower neighbor, so you don't see something very new yet. When we look at P1, the height becomes WP1 rather than P1, but the novelty starts coming in for the next point, P2 plus P1, because there you see how high do we take the second point, then we take all the distance down to the x-axis, P2 plus P1, and that we replace by its W value. That's how now we locate the second point. We go on like that. The third point, again, we have been transforming P3 plus P2 plus P1, distance all the way down to the x-axis, and we go on like that. The final point is level high. The height is 1, and we are transforming 1, and it remains 1. So a typical thing that you see in this figure is that the total height is not changed. And good mathematicians know if you change the total measure of a space, then you get violation of dominance. So mathematicians could have quite quickly. But anyway, this was what Quiggin proposed, and this is really the dual. If you want to do with probabilities what the economists do with outcomes and utilities, then this is what you should really do. So this was the formula that Quiggin proposed. And here is a figure again. Let's write in formula what the area is now that we did this. And we see this is, of course, the graph of a function, and then the integral of that function is the total area. You saw it before. So let us see what kind of function is this, the graph. We take a number alpha, then how high is this? This is now, before you saw it where it was P1 plus P2, but now we W transformed it. So now the height is the W of P1 plus P2. And that is the W of the probability of getting something higher than the outcome. So that means we're now in fact integrating the W transform of the rank function. But let me write it more algebraically. The first layer, total area, is WP1 times x1. The second layer, the total area, is x1 times the height. But the height is now the difference of two W values. It's WP2 plus P1 minus WP1. It goes on like that. Every layer, the height is the difference of two W values. For instance, the last one, the height is WP1 plus Pn minus the W of Pn minus 1 plus P1 times Xn. So that's how it works here. when using this concept of rank, the formula is not very nice. Maybe it's a bit complex, but using ranks makes it a bit simpler and easier. In fact, for instance, in each case, you can see that this difference of two W values, first you take the rank, and then you take the rank plus the outcome probability. In each case, for instance here, the W weight that is assigned to outcome xn is the W of Pn, the rank, your probability of getting a bad outcome is Pn minus 1 plus P1. So we have here the W of Pn plus Rn minus the W of Rn. And that's everywhere. Also for outcome x2, for instance, the rank is here P1 and the outcome probability is P2. So again, the weight is the marginal W contribution of the outcome plus the rank minus the rank. So that's a bit of a more tractable formula, and that's how you can better memorize it. But I guess you have been digesting enough information now. Let's now move on, and you have to study it as homework. But this was indeed a good formula. And well, it was first sight from mathematical intuition, a plausible formula that may make sense. If it's really good theory, you have to do much more work. You have to show that it empirically works well, that it fits data well, that it captures psychology of human beings, and that it has good preference foundations you want to get. But all those things have been done, and part of them I will tell you later in this course. But it turned out this was the right idea. This Quiggin idea, for the first time, we had really a behavioral theory. And I think the whole behavioral stream needed this. We need to connect psychology with theory. And here in this context of risk, it took creative, deep insight, and Quiggin provided. He had the right mathematical insight to really understand the formulas and really know how to do the analogy for probabilities, what economists had done with outcomes. In fact, the best thing is to combine the two, probably in general. Usually, you do not only transform the probabilities, but you take, especially if they're big outcomes, utility of outcomes can better be taken nonlinear. So then you combine the two. You do what we did before with outcomes, but now on the x-axis you take the u values of the outcomes. So you do the transformation on both axes. Then you get really the general theory of rank-dependent utility in full generality, and that's a very good formula. And then the value, we get that formula. The weights are again the marginal W contribution of the outcome probability to the ranks multiplied by the utility of the outcomes. And that is really a full generality, rank-dependent utility. For simplicity today, to explain to you the novelty of probability transformation, I was usually assuming linear utility, but in practice, especially for big outcomes, you want non-linear, for non-quantitative outcomes even more, you want non-linear, just general utility. That can be done. And it doesn't just everywhere what it did with outcomes, you do that then with the utility of outcomes. It doesn't really change much. So, but for simplicity, I did not talk about it, and you can study this formula and do homework with it. Then this formula is called rank-dependent utility, but it is in fact also prospect theory for gains. And prospect theory will later add that losses is a bit different, and empirically that's a good point to do. But this was really, in my opinion, the beginning of the behavioral approach. The first time that we had a really behavioral approach, and we needed the creativity of Quiggin to get it going. So glad we got it done. But with this, I finished chapter 5, the explanation. I took a whole hour to explain the formula, but I hope you get some feeling how this behavior works, that there's a psychology and a mathematics, they come together. And then we get very good theories. You can do all kind of quantitative predictions, but it's also empirically realistic. And now you've seen a first example in some depth of that happening. Well, more to come, but that will be in later meetings. This was the last thing of this third meeting, to be continued.